So in this video, I want to give an introduction to molecular polarity. So we've already talked about polarity in a bond, right? So if we have A bound to B, and let's just call B the more electronegative atom. Now remember what we said about the bond polarity, that the more negative side of the electron density will be pulled towards the more electronegative atom, right? So we can write our polar arrows like this, okay? Where this is where you have the more positive a more positive charge over by molecule A, and the more negative charge over by B. And it's the polarity arrow is pointing in the direction of where the electron density is going. So if we take this whole concept, and we've only done it with just in relation to one bond, but if we combine them with multiple bonds, we can get to an overall molecular polarity. And the reason this is important is because once we start talking about molecular polarity, we can start to decipher how molecules will interact with one another, right? So first let's just dive right into some examples. So first let's take CO2. So if we have CO2 here, and the best way to start out by doing this is to start with the Lewis structure, okay? So if we have C bound to 2 oxygens, right, you have 4 electrons from the carbon and 6 electrons from each oxygen, and this ends up giving you a double bonded carbon-oxygen bonds, with 2 lone pairs on each oxygen. And let's just make sure we have all of our electrons accounted for. So if we have 16 electrons that we need to keep track of, we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. Perfect. Okay. So now let's look at the carbon-oxygen bond alone, right? So if we zoom in to one carbon-oxygen bond, we have one bond going towards the oxygen, because remember, oxygen is the more electronegative atom. And we also have another polar arrow going towards the other oxygen. So even though both of these bonds are polar, with the electron density shifting towards the oxygen, right? You have this partial negative on each oxygen. Notice how these the two polar arrows are completely opposite to one another, thus they end up canceling each other out, right? So this is actually where this compound right here, this is an image from your book, that so you can see that the two polar arrows cancel one another out, making this an overall non-polar molecule. Right? So even though it contains 2 polar bonds, because those polar bonds are essentially pulling in opposite directions, it lends to an overall non-polar molecule. All right, so let's take our next example. So next we're going to look at what water might look like in terms of its polarity, okay? Again, this is just an image copied from your book here. It's just the ball and stick model of water. Okay, so if we were to draw the Lewis structure of water, we end up getting to a bent shape, right, with oxygen as the central, and then has 2 lone pairs up here on the oxygen. Now, if you're drawing the overall polarity, you can see in this picture here, it already has the polar arrows, but if we draw it ourselves, right? So we know that oxygen is the more electronegative atom in the OH bond, and so it's going to be, the polar arrow is going to be pointing towards the oxygen on both sides, okay? So notice how these two are not opposite to one another. If you were to add these up, these would actually compound to make an overall negative side for this molecule, and then this side of the molecule has a more positive side. So the electron density, because they don't cancel one another out, they make an overall polar molecule. So now let's take another example where we actually get out of the two-dimensional plane and we have to deal with a compound that is in more of a tetrahedral structure. So this is carbon tetrachloride here, CCl4. Now notice, and it's a little bit more difficult to see just when it's drawn flat like this, but if you have this carbon with two chlorines in the plane of the video, right, or the plane of the board, and then you have a wedge coming forward and then a dash going back, right, going back behind the plane of the board, you can see how the polarity in this instance can actually cancel out from one another, right? So you have these polar arrows with these carbon-chlorine bonds. Each carbon-chlorine bond has its own polarity, right? But then when you add all of these up, they actually all end up canceling one another, so you actually end up with an overall non-polar molecule. Okay. Now let's look at a very similar molecule. Now there's just one small difference between carbon tetrachloride and chloroform. Okay, it's CHCl3. So essentially all that we've done is replace one of the chlorine atoms with a hydrogen atom instead. Okay, so let's go ahead and draw out this chloroform molecule. So we can still draw polarity arrows, right? So carbon is less electronegative than chlorine. So we can draw these polarity arrows like this. But if you compare, if you look at the carbon-hydrogen bond, right, just the carbon-hydrogen bond, carbon is more electronegative than hydrogen, right? So it's going to be pulling on that electron density a little bit more than from the hydrogen, essentially taking it from the hydrogen. Now notice how this arrow is pointing in the opposite direction than this arrow was pointing from our carbon tetrachloride, right? So once we end up adding all of these arrows up with the chloroform molecule, then we end up getting to a compound that does in fact have a negative side on over here, where most of the electron density is pulled down to this side of the molecule, right? And we also have a partial positive up on this side of the molecule. So this gives us an overall polarity pointing down towards the chlorine side of the chloroform molecule. So this is a polar molecule. And this should pretty well get you started for determining how to apply polarity to molecular polarity. So you're really just comparing the polar bonds to one another, and if they all cancel out, as we saw with the carbon dioxide and the carbon tetrachloride, then you have an overall non-polar molecule. But if those polar bonds, the direction of polarity does not cancel out, then we end up having a polar molecule.